Fine. I think it's already 7 past 8. So we should start the class, although the number of students is only 100. I know it is hard Monday morning, especially after the long break. We are still in the sleeping mode, or many students will be in sleeping mode, so they might not join. So let's see, we'll continue, and whoever joins, let them join as the class proceeds. Hope you're able to hear my voice, students.
Yes, sir.
Yes, sir.
Yeah, thank you so much. Right. So in the last class, I have started storage of solids. One is open storage and cold storage. Then we have seen what are the merits and what are the problems associated with the cold storage. Why certain materials cannot be stored in a closed conditions. We have seen how they lead to fire hazards. We have seen. Then we have seen different types of closed storage. In that we have bins, hoopers, and silos. Then I have given a difference. Then I have showed an important slide, which I am putting here. I'm sharing the slides now. Hope you're able to see the screen.
Yes, sir.
Yeah. So then we have given to you important, we have come to important understanding that the way you store matters, because if you don't store the material in a proper vessel, it will not be easy to take it out. So we have to store material in a vessel. The design is such that the flowability, or we can take it out the material very easily. Of course, we have discussed extensively different flow problems in silos, arching, funnel flow, rat hole, flooding, and segregation. Because of segregation, non-uniform discharge or buckling can happen. So we have to avoid these things. Rather, we wanted a uniform flow like this. We wanted an uniform flow like this. All the particles should move continuously. I have also explained rotary valve. And while discussing this, how to avoid segregation, I have explained. How to avoid segregation, I have explained. So these are the segregation problems, and these are the way we can avoid the segregation. This we have explained. So segregation, if you have an intermediate wedge like this, can avoid the segregation. However, arching, funnel flow, or rat holing needs to be included in the design part. Now, one way to understand the flowability of the material, I have explained with the help of angle of repose. At the end, one student has asked me, I could not understand the C1. Probably I missed to explain or what, I don't know. So the C method, dynamic angle of repose. So this is a circular plate. This is a circular plate. We just put a material. Whatever solids we want, we put a material. We rotate at a constant speed. If you rotate in a plate, in a horizontal plate like this, you put the solids. With the time, you will see that the solids all tend to move one side. So if you spread the solids initially throughout the plate and you rotate, the solids tend to move and it will come to one side and make this kind of distinct boundary. The slope of this boundary with the horizontal axis is nothing but the angle of repose. the slope of the, let's say this is the horizontal plane, the angle is nothing but the angle of repose. That is also a simple way to test the angle of repose. You put the solid in horizontal plate and rotate at a constant speed. After such a time, we observe that the solids all tend to move one side and make a distinct boundary like this. Now the angle from the horizontal plane or the central plane will be nothing but the angle of repose. That is simple. And based on angle of repose, we can understand the flow behavior. However, there is no relation. It doesn't correlate. Angle of repose doesn't correlate with the Hooper angle in the silos. So what are the factors influences the flow of particles apart from the angle of repose? One is stresses in the bulk solids. What type of stresses? Internal friction and cohesive forces. Wall friction, that is friction between particles and the material used for the construction of silos. Compressibility and process conditions like temperature, humidity, and time consolidation. So we have started with stresses in bulk solids. We will continue to see all other parameters, how they affect in the flowability of the particles. So we have also explained, I have explained bulk density in the last class. Then I have explained the forces. So students, before I move on, does anyone have any questions based on the last class? I can take one or two, then move on to the next topic. If no questions, we will proceed forward. Okay, it seems there are no questions and we all understood whatever I'm explaining. Yeah, one important suggestion I wanted to give to all of you is that you all know that this is an online semester and there is a periodic or a continuous evaluation will be takes place, and exams will be conducted during the class hours, right? So you know all the tests will come at once. I request all of you, I'm sure you have done in 10+2, that regularly studying whatever being taught in that day. If you follow the same practice, it will really save you a lot of time and effort, and you will get grades very easily. So please review the slides or textbook, whatever I'm giving, whatever we are teaching on the day when we taught. When if you read on the day when you taught, you will be able to understand very fast and you will be able to remember for a long time. So one important thing I wanted to tell before I proceed. So this is the book, okay? Last class I forgot to mention. This is the book I used to teach the storage of bulk solids. Powders and bulk solids, behavior, characterization, storage and flow by Shule. So please, you all can, this is available online. So please download with whatever sources you have. And this is a huge book and it covers a lot of topics. This alone can be covered in throughout the semester. But that is not possible for me because of the semester and time constraints. I will have to teach many topics for you. So that's why I'm only covering the important portions which is needed at a chemical engineer, which are needed as a chemical engineer. Because that book can go into very in-depth analysis of the solid mechanics or particle mechanics, which is not possible for me to entirely cover the book because of the time constraint. So I'm giving the major portions of the book. So obviously you can understand yourself if you if you are interested to explore further on this topic. But I'm covering the essences of all the topics, so don't need to read whole the book. And whatever portions I am teaching, if you read from the book, that will be sufficient. So maybe in the next class, which are the chapters I have, which are the chapters or which are the page numbers of important, I will also mention, so that your reading will be easier. Right. So we'll move on from here. So let's say the force is acting in the inclination, certain angle. The normal force acts in the direction, and shear force acts in the direction. Shear force per the area is shear stress. Normal force per area is the normal stress, and shear stress emerges due to the frictional effects. Shear stress emerges due to the frictional effects, either friction between the individual particles, that is due to the interaction between individual particles, or the friction between the particle and the solid surface, that is the interaction between the particle and the solid surface. So I have given an example here, that is an interaction between particle and solid surface, how that is being causing a shear stress. That's what I've shown here. So here we have a plate, right? And on that there is some bulk solid at rest. The angle of inclination is 0 because the plate is in horizontal direction. When I tilt it slightly, when I tilt this plate slightly, we can observe that there is no movement in the particles. Why are that they're not moving? Because obviously, as soon as you tilt, the particle should flow down because of the gravitational force, right? As soon as you tilt it, the particle should flow down because of the gravitational force. But why are that they're not flowing out? Because of the some resistance is offered in the opposite direction of the gravitational force. The gravitational force is supposed to act in this direction, Fg. But the solids are not flowing out. Still solids are at rest because some resistance being offered by the particles. So what kind of resistances? That is either internal friction between the or interaction between the particles are obstructing the flow, or the interaction between the particles and the solid wall is also obstructing the flow, right? If I tilt it further, what is observed? The bulk solids have started tending to move downwards. That means the gravity force which is acting the downwards is overcome the resistance offered by the particles. That is, the resistance offered is either due to the friction between bulk solids and the friction between bulk solids and the surface. So that is where the interaction between these particles and the surface wall comes in terms of the shear stress effects. The force acting on the solid, you can see the force acting on the solid is the normal stress. The force acting or the resistance of the solids is shear stress. Hope you all understood. This is very, very simple, and it's very important for us, either in fluid mechanics or here. This basic understanding will always important. Okay, so you all understood, I guess. Now there are different stresses in bulk solids can happen. So let's say we have a we have a hollow cylinder like this. We have a hollow cylinder, and we have this is a cylinder, and particles, some solids are kept, and some vertical stress sigma v is applied in this direction. Same vertical stress is also applied in this direction. Now, can anyone say, when you apply stress in this direction, there is some stress also acts in the horizontal direction. Although this is solid wall, we are not externally applying. The horizontal stresses are not externally applying, but as soon as we apply some external stress, there will be some horizontal stresses also. There will be some horizontal stresses also. Why is that? So this is the, let's say this is the cylindrical material, and these are the particles. Right? If when you apply stress from the top, what do you think? What will happen? All the solids compress in the uniform direction. Like is all the solids are moved in same direction? In case of fluid, that is S. Let's say this is the liquid, and you applied some pressure, and all the fluid moves, because the pressure in the liquids and gases acts uniform, but whereas the pressures in the solids will not act uniformly. Because the movement between particles will not be continuously uniform. Between the particles will not be uniform because of the internal friction between particles and internal friction between the solid wall and the particles. Some stress distributes in the horizontal directions also. Some stress will distribute in the horizontal direction also. Even if there is no external horizontal stress, when you apply some vertical stress in the vertical direction, because of the internal friction between the solids, it will distribute, some stress will distribute in the horizontal direction also. That's why the horizontal stress also acts due to the vertical stress. That horizontal stress versus vertical stress is known as lateral stress ratio. Lateral stress ratio will be a constant at a certain conditions for a given material. Lateral stress ratio will be a constant for a certain material at a given conditions. Some books denotes this as a K, and some books this denotes as a lambda. So both are lateral stress ratio. Often they use K, but sometimes they refer with the lambda also. The K values typically varies from 0.3 to 0.6. The K value typically varies from 0.3 to the 0.6. Hope you all understood vertical stress and horizontal stresses. Anyone could not understand, kindly let me know. Okay, good number. Right. Now, so hope you understood the difference between the flow behavior of solids and the flow behavior of liquids, which I explained in the previous section. Another important behavior is elastic and plastic deformation. These are all. I have to teach all these basic concepts, and this will be a theory part. So kindly pay some attention. Kindly pay some attention. I know it is hard to look at your screen in a mobile and read a lot of text and a lot of theoretical classes, but unless I explain the foundations, the concepts very well, there is no point of solving a lot of problems without understanding basic concepts. We have to do both, conceptual understanding and problem solving. Both has to be strengthened. And this whatever concepts I'm explaining, they're very, very important. They often you encounter when you deal with real-time problems. Elastic and plastic deformation. Probably you know it, but let me explain once again. If you know it, please let me know. I can skip. Otherwise, I will just explain in a quick manner. Right. Elastic deformation. Okay. This is the elastic deformation. Elastic deformation occurs when load, that is a normal stress, when load is applied, deformation takes place. When load is applied, deformation takes place. That all of us know. And the deformation disappears completely after the load is removed. Just like the elastic rubber band. When you apply load, that will stretch. The stretching is deformation. The stretching is deformation. When you release that external load on the elastic rubber band, what will happen? It will come back to the original state. It will come back to the original state. That means the deformation disappeared. The deformation disappeared. So this is the same thing is expressed in terms of a graphical representation. The same thing is represented in graphical representation. This one, A, the graph A. So this is stress. So as I said, this is the rubber band. If you apply some stress, that is, we have pulled. Let's say you have pulled with some stress. So as you apply stress, means as you put more and more amount of force, then what will happen? This will stretch. This will stretch. This will stretch. The stretching is expressed in terms of strain. The stretching is expressed in terms of strain. Change in length by the original length. Change in length by original length. That is called strain. So as you apply more and more stress, the deformation, the strain increases in the forward direction. When you release the stress, that is, when you release the stress, it will come back to the original. As you decrease the stress, the strain also decreases and come to the original state. Such materials are called elastic material. Such materials called elastic material. Gases, right? The gases behaves elastic nature. The liquids behave in elastic nature, which are compressible liquids, and which behaves in elastic nature. But solids will never show the elastic deformation behavior. The solids will never show the elastic behavior. So the behavior shown by solids is often called plastic deformation. The deformation behavior shown by the solids is often called plastic deformation. So what will happen that when you apply some load, that is, when you apply some load, certain compression will take place or expansion will take place. Compression or expansion will take place. Like, so let's say I have a plate and I have some solid like this. I have some solid like this. And I'm just putting some weight. Let's say I'm putting some weight and I am compressing it. I am compressing. What will happen? The powder tend to expand. Let's say this is the vessel or whatever. That is one. Another way. That is one example. Another example is this is the hollow cylinder, and we have kept solid particles, and we are applying some load. We are applying some load on this one. When you apply some load, what will happen? The powders tend to get compressed. The powders tend to get compressed. Because of the compression, the delta H height changes, right? The delta H height changes. This delta H by H is nothing but the strain. The delta H by H is nothing but the strain. Delta H by H is nothing but the strain. As you apply stress, the strain increases. The strain increases. Right? In case of elastic deformation, it will go linearly. But in case of plastic deformation, it will go linearly up to some point. Then once it reached a certain stress value, it will show an exponential behavior. It will show. So this is linear. This is the linear. And this is from here it will change into the exponential form. It will change in the exponential form. Let's say you have stopped. Let's say we have stopped applying the stress at this point, and this is the strain, the maximum strain level it reached. The maximum strain level it reached. When you remove the stress, it will not go back to the original state. It will not go back to the original zero state. Rather, it will go linearly and retains the certain stress. Means whatever deformation is happened, that will not come back to the original state. Whatever deformation is happened, that will not bring back to the original state. So such deformations are called plastic deformation. Such deformation is called plastic deformation. Okay, hope you are understanding. I'm not boring you. So one such example is compaction, right? Compaction. When you apply load, here I've just plotted some strain. We just plotted versus delta H, especially tablet manufacturing. In the tablet manufacturing, what they will do? They will take a punch disc. So there's a small disc. This is a small disc like this, whatever shown here, and you fill the tablet powder. Then you apply sufficient stress that will go back to the compaction. There will be compaction takes place. When you're loading, as you are applying stress, compaction takes place. As you are applying the stress, compaction takes place. But once you attain the certain compaction level, when you remove the load, when you're doing the unloading or when you remove the stress, it won't change the height. The delta H value will be remains same. So this is called compaction. Especially briquettes manufacturing, tablets manufacturing, pharmaceutical industries, they use this compaction principle. So they will identify at what stress, at what extent we need to go, so that we will have a compacted structure which will not change, which will not deform so easily. That is what very important, especially when you do the briquetting and the tabletting industries or tableting in the pharmaceutical industries. Students are able to understand what I'm trying to explain?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
That is good.
Sir,
Thank you.
could you repeat the compaction part once?
Sure. So compaction. So this is a hollow cylinder. So it has a bottom surface. And initially you have filled everything with the solids. We have filled whole area with the solids. Then with certain like a piston, you have applied with certain stress, force per unit area. So this vertical stress, the vertical stress multiplied by area is nothing but the force with which we are moving the piston. The force with which we are moving the piston is nothing but vertical stress multiplied by area. The force with which we are moving the piston is nothing but vertical stress multiplied by area. When you move the piston downwards, the compaction takes place, right? The particles tend to come closer, depends on the particle size. The particles come closer. So because of that compaction, the delta H is changing. As you apply load, let's say you applied this much load, this much delta H variation is taking place. As you apply more and more load, and more compaction takes place. And it goes up to certain extent. When you apply to certain loading, the full compaction takes place. When we say full compaction takes place, when I remove the stress, when I pull back the piston, unloading means when I pull back the piston, when I release the stress, you will see that whatever let's say at this point, and in this compaction, this is the level. This is the level. At this the peak point, this is the level. So this is the final delta H, let's say delta HF. So this is the delta HF. Delta HF, right? When I release the stress, when I pull back the piston, it will not 100% always have the whatever final. There will be slight, since we're applying, there will be slight change, and it will retain the delta H. Means once I pull back the piston outside, I will see that very slight increase, but it will not come back to the original state. It will not come back to the, this is the original state, right? This is the original state. And this is the compacted one. This is this type of technique, compaction technique, used in the tablet manufacturing. We all take tablets, right? Paracetamol tablets or whatever tablets. That tablets manufactured in pharmaceutical industry uses this compaction principle. So, and also briquettes. Briquettes manufacturing also use this compaction principle. Do you understood? The student who asked the question.
Yes, sir.
Did you got the compaction?
Yes, sir.
Thank you. Now, another important thing is adhesive forces. So I previously told the interaction with particles. What type of interaction is possible The interactive forces between the particles is also known as adhesive forces. So the flowability of finely grained, fine grained means very fine, very small size particles largely depends upon adhesive forces, whereas coarse solids will not have much adhesive forces. The coarse solids will not give much issues with the adhesive forces, but whereas fine grained, fine size bulk solids will largely depends upon the adhesive forces. Example, agglomeration between the particles, right? Agglomeration processes. How particles tend to agglomerate? Because of these adhesive forces, they all come close together. All the particles are come close together. All particles are come close together, forms an agglomerate. And also powder coating, right? We all know nowadays we use the powder coating, cars, almirahs, everywhere. So when you coat certain material, let's say this is the stainless steel, and you have done the powder coating, a thin powder coating. Whatever the coated material should adhere to the metal surface. So the adhesive forces makes the coating to stick to the strong. And blackboard chalk, right? When we write with the chalk on a blackboard, the the chalk material should stick onto the board surface. If you have an extremely smooth board, definitely you will not be able to write. It will not stick, right? So that's why the sticky nature, the addition of the sticky nature or whatever, when you write with the chalk on a blackboard, it stick to the surface. When you apply some force, that is with the duster or eraser, all those particles will come out. So that is the interaction, adhesive forces between the chalk particles and the blackboard. And for the cosmetic powders, right? When you apply some cosmetic powders on our skin, the cosmetic powder should stick onto your skin surface. Of course, what are all, how to create the adhesive forces, that all I'm not talking. I'm just giving that there are importance of the adhesive forces. Interaction between the particles and the surfaces, and between the particles and the particles. That is what I'm trying to explain. I'm giving examples here to give an understanding, interaction between surface and the solid particles, and interaction between the particles, right? When you do the powder coating, there has to be strong interaction between the powder which you are coated with respect to the material on which the powder is coated. That is metal surface and the paint. The interaction will be very strong. The interaction between the chalk and blackboard has to be there. Otherwise, they will not stick and you will not be able to see any letters. Similarly, cosmetic powders, interaction with the skin has to be sufficient enough so that will stay on the skin. Otherwise, no brightness, nothing. There won't be any use of the cosmetic powders, right? So these are the 4 examples I'm just given to show that there is some interaction between particles in the powder and the particles in the surfaces, right? So with fine grind means when we have the, as I said, only for the fine particles, small particle sizes of the micron range, the adhesive forces plays a role. But the particles of millimeter range, adhesive forces will not be majorly dominating. Adhesive forces will not dominate if we have the coarse particles, that is in the millimeter size. With the particles in the micron size, definitely the adhesive forces plays a major role. So with dry solids, right? If you take a purely there is no moisture, completely dry solids, the major adhesive forces are van der Waals interactions. The interaction between fine particles, if the particles are dry, the forces is van der Waals interaction. What are the van der Waals interactions? I think you know, or you will learn more in detail in thermodynamics, but in a quick way, any weak intramolecular interactions, For example, suppose we have a lone pair electrons. If we have a lone pair electrons in one molecule, one atom can interact with other atoms, and if you have a positive surface charge on some molecule can interact with the negative surface charge molecule. So any weak intramolecular interactions, any weak intramolecular interactions are called van der Waals interactions. Electrostatic forces. Electrostatic forces. We all know that when every material will have certain static forces, not we can create on the surface, right? Two extreme conductors and insulators. So based on the surface charge, the molecules also tend to interact with each other. We all know that the particles of different charge, opposite charge, will come close together and attach together. So that is the adhesive forces. These are for the dry solids. With the moist bulk solids, that is, we have solids, but there is some moisture with them. There is some moisture, wet, not completely wet like suspension, but there is some significant amount of moisture is present. 5%, 10% amount of moisture is present. If the solids are moist, then what dominates? What adhesive force dominates? The liquid bridge between the particles. This is one particle, this is another particle. So this is one particle, this is another particle, and the liquid bridge between this and the capillary pressure, the capillary force between this one makes them, the surface tension between the particles makes them stick to each other. And once you have moist solids, van der Waals interactions, electrostatic factors will not play a role at all, will not play any dominating roles. Totally, the liquid bridge between the particles plays the more dominance or major role. Right? So these are the adhesive forces. I'm just giving an example how to estimate these adhesive forces. There are a lot of data available, with experimental data available. So one example I have shown here, if you take a spherical particles of 10 microns, and this is the surface, If the particle at a distance of A, if the distance between particle and the surface is A, and if it is moist solid, of course, here they given different. The graph one, the line one is for the liquid bridge. One thing you can understand that as the distance increases, the adhesive forces are decreasing. As the distance between the particle and the surface increases, the adhesive forces increasing. And you know, the pore size, the void fraction, like if you place solids, there will be void fraction, right? There will be void fraction. The void fraction between solids will be higher. The void fraction between solids is higher for the higher particle size. So if you have a core solids, right? If you have core solids, definitely the void fraction will be more. The distance between the particle to particle will be more, and the distance between particle to the solid also more. Hence, the adhesive forces will be less effective, less dominating. But if you have fine particles, since fine particles can pack very closely to each other, the voids, the gap between the particles will be very low. Hence, adhesive forces can be play crucial role. So if it is liquid bits, this graph, and if it is electrostatic forces for a conductor material, this one, and if we have a for insulated material, one, and this is for the if van der Waals force are the dominating, and this is the one. So we can see that one important thing we have to understand that the adhesive forces purely depends upon the distance between particles or distance between the particle and the metal surface. I just explained before, so I don't need to explain. So one of the important effects is one of the important effects, a very popular effect is called lotus effect. Have anyone heard about lotus effect?
No, sir.
Okay. So probably you all seen lotus leaf. This is the lotus leaf. When I put a droplet of water, in a lotus leaf, what will happen? When you put a droplet of water, it will show the drop will not interact with the leaf. The drop will not interact with the leaf. Why? Because of the hydrophobic nature. Because of the hydrophobic nature. What is there are two things, right? We have a polar and non-polar, and we have hydrophobic and hydrophilic. Polar is water loving and hydrophilic is also water loving. Water loving materials means it will absorb moisture immediately. As soon as put in a water, it will absorb moisture immediately. They are called hydrophilic materials. Example is paper. If you take a paper, as soon as dip in water, what will happen? The paper adsorbs. The water because of its hydrophilic nature. The carboxylic groups present on the paper surface loves water. It takes immediately interacts with hydrogen bonding, interaction between OH and hydrogen carboxylic groups and hydrogen in the water molecule interacts very fast and it pulls out the water. Now other ones is called hydrophobic. Like if you take a polythene, right? If you dip inside water, it will not absorb any moisture. It won't absorb any moisture because the polymer is hydrophobic surface. The interaction on the surface functional groups of the plastic doesn't interact with the water molecules. So they're called hydrophobic. So in the lotus leaf, there is a wax coating. There will be a fine wax coating on the surface, and that fine wax coating makes the hydrophobic nature. But however, lotus leaf possesses super hydrophobic, not just hydrophobic. Super hydrophobic means as soon as you tilt the leaf, what will happen? All the water droplets will fall down. As soon as you tilt the leaf, what will happen? All the water droplets will fall down. There is small difference between hydrophobic and super hydrophobic, right? Hydrophobic means it doesn't absorb water. But at the same time, the droplet will not fall down as soon as you tilt it. Just small tilting can make sure that all the droplets will go from the lotus leaf. Why is that? If people have observed under microscope. When we see under microscope this lotus leaf, they have found out that there are a lot of spikes. Sorry, the image is not clear. That's why I have kept an image and a graphical representation. There are the spikes. These are the spikes. Instead of the leaf in a planar surface, what will happen? There are the spikes. So these spikes Because of the spikes, and also on the surface of the spikes, there will be wax crystalloids. And because of the spikes, there is some air here. There are some air pockets. And this is the gap between these two pockets are very small in the nanoscale. The gaps between the gap between these two will be very small, maybe 1 micron or lower, often in the nanoscale, right? So when the droplet comes here, that will sit on this, spikes. Since there is a huge gap, because of the spikes, as I shown earlier in the previous graph, if the gap between the material, the surface and the material, the particle is very high, the adhesive forces will not be playing, it will not dominate. Adhesive forces will not dominate. Because of the spikes, because of this gap between the bottom surface to the droplet, adhesive forces will not make any major dominance role here. Because of the spikes, and there is less adhesion forces effect, and because of the hydrophobic nature, and because of the spikes, which is causing the less dominance of adhesion forces, that makes the super hydrophobic material. That makes the lotus leaf as a super hydrophobic material. So why do we use super hydrophobic material for self-cleaning? Let's say on the surface we have a dirt. Let's say we have the dirt. When you put the droplet, we know the droplet will roll, right? We know the super hydrophobic surfaces, as I said, the droplets, as soon as you tilt it, the droplets will fall down. The droplet will roll. As the droplet rolls, it collects all the dirt particles and take it away. So that is an advantage with the super hydrophobic nature, and especially with the self-cleaning properties. If you want to achieve super hydrophobic nature, you need to have two things. One is hydrophobic surface. Just hydrophobic surface is not sufficient. So, for example, if you take a plastic container, right? If you take a plastic container, you just put a drop of water. You know that water will not stick, water will not be absorbed. But if you tilt it, the droplets will not fall down. So easily. What will happen? The droplet will tend to coalesce each other, then make a thin layer, then the layer will fall down with time to time. The layer will fall, or the layer will stick on the surface. Hope I'm giving. Hope you're understanding. Let's say this is the plastic. Let's say you take a plastic bucket, and you just put water droplets. Then you see the water droplets are like this. Because of hydrophobic nature, the water will not be absorbed by the plastic. But when you tilt it, slightly, you will see that it will not roll out. Drops will not roll out very fast. The drops will not roll out like lotus leaf. What will happen? The drops drop, first coalesces, then forms a film. Then the film will slowly fall out from the surface. So that's what we observe. Although the plastic is a hydrophobic material, because the buckets what we see will have a very smooth surface, which will not have the hydrophobic effect. Similarly, in the lotus leaf, not only hydrophobic nature, because of the spikes, it reduces the adhesive forces effect, because adhesive forces is totally depends on the distance between the particle and surfaces, and it minimizes the adhesion effect. That's why the water droplets roll out. Very fast, and that is used for the self-cleaning applications. Student, we understood lotus effect and self-cleaning properties.
So, self-cleaning property, what is the use of self-cleaning property?
So let's say this is the surface, right? And it has a dust. With time, the dust particles coming and sticking on the surface, right? If you do the self-cloning properties, what will happen? If you just put a drop of water, the drop will rotate, right? The drop will rotate. As the drop rotates, it collects all the dust particles and go it away. And drop will not stick. You don't need to wipe it again. Especially, you just spray water and all the things will fall down. All the things will be collected. That is one. Another one is that the particles, as soon as it comes, because of the super hydrophobic nature, the dust particles will not stick initially. It just stick. It will just fall down as soon as falls on the surface. I'm giving two reasons. One is that, let's say I have a surface. Let's say you have medical equipment, right? And medical equipment, and time you need to clean it. Because of the dust in the environment, the dust can come and stick it. Very fine dust can come and stick onto it. Okay. So if you just put a drop of water, what will happen? The drop of water, as it rolls out, it collects, and drop of water falls out. No drop will stick onto the surface. So you don't need to have an additional effort to clean it. The cleaning will take place by itself. That is one. You may say, why? Then I'm spraying, right? Then you may say, I'm spraying. So we also know that in a daytime or in a day, certain time we have condensation and certain time we have the droplet formation takes place, right? In the moisture in the environment itself can form the droplets. The moisture in the environment can make the droplet formation on any surface, right? So let's say during daytime, this is surface. During daytime, some data particles are sticking on surface. And obviously in nighttime, we see some precipitation of the droplets takes place on most of the surfaces. So as soon as the droplet precipitation, the droplet will not stick, rather droplets will come and collect it and the particle will be cleaned. So that the self-cleaning will take place by itself with natural environmental effects. Natural environmental effects can lead to the self-cleaning of the instruments or whatever surfaces. Do you understand what I'm trying to explain? Am I answering the
Yes,
question?
sir. Yes, sir.
Okay. So that is it. So adhesive forces or interaction plays a major role. So I think we will take a 3 minutes break here. Right? All of you can bring some water, use washroom. Then we'll continue from this one. All right, students, we'll take quick 3 minutes break just for drinking water or using washroom. Then we'll continue. Yeah, students, let us start again. So, as I mentioned here, so if you want to get superhydrophobic surfaces, you need spikes like material. So to achieve that, people often coat metal nanoparticles on the surface, and that can lead to the superhydrophobic nature, right? The next one is uniaxial compression stress. So, so this is a hollow cylinder, right? This is like a hollow cylinder. And just represent the cross section here. Now the hollow cylinder is filled with particles. So this is all the particles. From the top, like a piston arrangement, we are doing certain compression. We are applying some force. As you know, stress is force per area. Stress into area is nothing but force. Now, we are applying certain force. When you apply certain force, what will happen? There will be some amount of compaction, right? There will be some amount of compaction takes place. After certain amount of compaction, the hollow cylinder was removed. That's why there is no metal surface here. Here initially certain amount of compaction was done, right? After certain amount of compaction, the hollow cylinder is removed. Okay, so here now we have only a compacted solid. Here we have only compacted solid. Initially powder bulk solids. The compaction is done to create a certain addition and make a compact solid. On this compact solid, if you apply, if you keep applying load, what do you observe? At some critical load, at some critical stress, the compacted solid will break. The compacted solid will tend to failure. The stress at which the compacted solid breaks a failure, that is called compressive strength. Strength is the maximum load, right? The maximum stress. Strength is nothing but the maximum stress. So compressive strength is the maximum stress at which the compacted solid tend to failure. That is also called as cohesive strength. That is also called as unconfined yield strength. Unconfined means yielding, the failure or breaking of the material will not be unconfined to only one zone, only one region. That's why it's also called as unconfined yield strength. In the book or in the stress behavior in solids, this word is commonly used. Why this commonly used? We are interested in the flow behavior, the flow of particles, right? When it's tend to break, breaking means what? Failure means what? The specimen starts to flow. Initially compacted, all staying together. All particles are staying together. But when you apply certain load, the failure, the compaction broke. That means the particles tend to move apart, flow apart. So unconfined yield strength is very important to understand at what conditions the bulk solids will tend to move. At what conditions the bulk solids will tend to move. If the load what we are applying from the vertical direction should be higher than unconfined yield strength. If it is crosses the unconfined yield strength, then only the particles will move out from the silo. So this is the storage. This is the storage, right? All particles are cohesively adhering to each other. All particles are cohesively adhering to each other. Depends upon the size and adhesion forces, many factors. If the load is applied on this one, if the load or stress is applied on this one, should be higher than this unconfined yield strength, then only that load or stress can break the confined nature between the particles, and the particles can start flowing out. The particle can start flowing out. That is why it is very important for us to measure this unconfined yield strength. So I have given a small
Sir,
concept. Yes.
sir, but like the initial compaction that we are doing will not affect the unconfined yield strength. Like
Yes,
if we close it tighter,
you are
then
absolutely right. The how much unconfined yield strength is completely depend upon the how much compaction we have done. That is exactly right. That is what your question, right?
yes, sir, yes.
Yeah, it is the unconfined yield strength is totally depends upon the initial consolidation. So for the testing, whatever amount of consolidation is taking place in the silos, same amount of consolidation has to be done by testing.
Okay, sir.
Thank you. Thank you for raising important point. So kindly mute your mic. So same thing. Whatever the student has rightly pointed out, I'm just putting the same one. The unconfined yield strength is depends upon the initial consolidation stress. Initial consolidation stress. If you apply more consolidation or compact, the stress used for the compaction, as if you put more amount of load for the compaction, the bulk density, the packing between the particles will be more. Hence, the bulk density will also increase. Along with bulk density, if you put more compaction or consolidation stress, you will have the more unconfined yield strength. For usually for most of the materials, it follow like a curve. It follow like a curve, but some solids also, there are very rare few solids also observe B type of material. Only difference is that it goes variation, but sudden rise after certain compaction will take place, especially because of the dominating adhesive forces. So these two types of curves are observed with the variation between the compaction or the consolidation stress with respect to the unconfined yield stress. That is one. Another thing also affects is time. So let's say you have this is a silo, and we have stored the material. And at zero time, you have measured a relation between unconfined yield strength versus consolidation or compaction stress. So this is the curve what you have seen earlier has come. At just you took the material, you kept in a silo, and at the same conditions you got this. If you leave it in the silo for some time, let's say at T1 days, right? If we measure the relation between unconfined yield strength versus consolidation stress, that is compaction stress, you will see a different. Sometimes you see same curve, or sometimes you see a different curve of higher. Why? With time, see, these are all particles stored in its silos, right? These are all particles stored in silos. And you know, this is very tall. This is very tall. And we all know that mg, the gravitational force, acts on the downwards. So the solids at the bottom, will always under certain load. Will always under certain load. Because of the load, and because various other factors, what will happen? More and more interaction, more and more compaction takes place. More and more compaction can takes place. That is why if you store solids for longer time, the unconfined yield strength versus compaction stress, the graph will increase. The graph will increase further. It depends upon, not only depends on the unconfined yield strength, that is the strength at which the compacted solid failures, breaks, that is not only depends on the compact strength or consolidation stress or compact stress, it also depends on the time. This effect, this time effect, is known as time consolidation. Time consolidation. Certain materials, it may not vary. Like if you take a dry sand, if you take a dry sand, store it in silos, if you leave it for 1 month also, this even after 1 month, the line will be same as A only. The line will be same as A only. But for some materials like gypsum, sulfur powders, the curve, the sigma C versus sigma 1 curve will change with respect to time. The sigma C versus sigma curve will change with respect to time. That effect is called time consolidation. Now, like we have given the flowability based on the
Sir,
angle of
what is the instantaneous flow function and what is time flow function?
right. So at 0 time, that is called instantaneous flow function. The flow function is, as I just mentioned, if the sigma 1 or the load what we have applied, if it is more than the unconfined yield strength, what will happen? Failure takes place. The particle will tend to move, right? That's why the graph between unconfined yield strength versus the compact stress is also known as the flow function. Right? We have an empty silo. We just store the solids. We just pour the solids. That is at the 0 time. And if you just open it, instantaneously it will flow, right? Depends on the conditions. So that's what it's called, instantaneous flow function. But if you store solids for some time, then you want to take it out. Then you want to take out the solids. But the same conditions, the conditions are changing. The unconfined yield strength is changing, increasing with respect to time. And that's what they call time flow functions. That's what we call time flow function. Flow function is the graph between this versus this. At 0 time, instantaneous. With time, if the compaction takes place or consolidation takes place, that is called time flow functions. Did I answer your question, student?
Yes, sir.
Have you understood what I'm trying to explain?
Yes, sir. Yes, sir.
So just like we have a flowability can be found out using the angle of repose, and more accurate way we can understand the flowability from this factor called FFC. This is the ratio of this is the ratio of the stress, vertical stress acting, that is the compact stress versus the stress at which we have compacted the material versus the unconfined yield strength, that is the maximum stress at which the particle tend to failure or the particles tend to flow. So this is FFC. If FFC is 1, that means what? This is very high. The critical unconfined yield strength is very high. Then the particles will not flow. The particles will not flow. If between 1 to 2, very cohesive means it will move but slowly and like a blobs, it will tend to move. Between 4 to 10, easy flowing, above 10, free flowing, complete mass flow. Very easily the particles will tend to flow down. If we have this, the vertical stress what you are applying should be much higher than this unconfined yield strength. Right? Unconfined yield strength. Then the particles will flow. This previous, the flow function, this sigma c versus sigma 1 is a graph, right? In the graph also we can represent. Like if you apply, if the conditions are like this, then you will see very cohesive flow. If the conditions are better flow than the previous one, the flow will be better than this one. If you put more and more, and bring back to the 10 condition, of course depends on the material, then it will be better. So not flowing, if the particles are not flowing, is one condition, and if it is flowing, cohesive flowing, it is acceptable. The cohesive flowing is also acceptable, but not flowing conditions are not at all acceptable. So if you maintain not flowing conditions, that is this one is less than this one, right? The vertical stress on this is silo, and this is the vertical stress what you are applying. Okay, this vertical stress is lower than this unconfined yield strength. What will happen? Even if open, even if there is opening at the outlet, the particles will not flow. The particles will not flow. You may say how this particle will stop flowing. Instead of particle to come out, there will be bridge. There will be a bridge formation. That bridge is called arching. That condition is called arching. I showed, right, in the last class, one of the flow obstruction is arching. Arching when will happen? If the vertical load on the silos, if it is less than unconfined yield strength, instead of particles to come outside, the flow obstruction called arching will happen. Same thing I'm explaining here. So this is a typical silo, right? Typical silo will have a vertical cylinder, then we have a tapered bottom. The tapered bottom is for the removal, a continuous removal of the particle. It helps in the flowability of the particles. So in silo design, the top part is only important when you talk about the stress conditions, but flowability conditions entirely depends upon the cone only. The flowability conditions entirely depends upon the cone only. Right? So let us see only cone portion. So since this is only the place, this only cone portion influences the flowability of the silos in a silo design. So I have only taken the cone portion. So instead of let's say instead of taking an opening one, let us take a closed. For example, for initial illustration point of view, let us take the closed one. Like we have a very narrow, very small opening, almost like zero. So if the height from the bottommost point is as height increasing, so this is the height from the 0 point. And if I plot graph between whatever vertical load is acting, whatever vertical load is acting at that point, let's say at this height. So on the solids, how much vertical load is acting, whether it's gravity or by external load, let's say that is sigma 1. And for this material, using the uniaxial compression test, we can also estimate unconfined yield strength. If you plot a graph, let's see, usually it won't be a straight line, but just to explain the concept, I have kept a straight line. Later we will derive the profiles and I will show you what kind of profile and how it looks like. So this is the vertical load acting with respect to the distance. You know, at this point, the whatever the load with which the particle will come out will be very zero because there is no opening, right? As the opening increases, and the height increases, and this will increase. Similarly, the unconfined yield strength will be like this. Now we know the ratio between this versus this is the flow factor, right? See. So if you plot FFC, that is the ratio of unconfined yield strength versus compressive stress or consolidation stress, that will be FFC. The graph looks like this. So suppose if I take a line here, instead of a complete tapered cone, instead of a cone, this is the tapered cone. That means the silo has this much opening. If the silo has this much opening, you see that FFC value is almost close to 1. Then it can flow. But if it is 1, the particles will not flow. But if you have a better gap, the flowability will be increases. So in silo design, the opening, the discharge opening, the outlet opening plays a critical role in determining the flowability. So in silo design, two important things: with what angle what is the Hooper angle, what is the slant angle, and what is the diameter of the outlets. If you design these two properly, you will always achieve a free flowing material or a continuous flowing of the material. So if it is 1, if FFC is 1, as I put it close to 1, if FFC is 1, what will happen? Since the flowability conditions are not favoring, the particles cannot flow out, and the natural way to obstruct the flow is by arching. Whatever solids coming out that form like a bridge, that is called arching. So I have showed earlier one of the flow obstruction problem is arching. Student, do you understood arching?
So I have a doubt. So,
Yes.
sir, can you please help me understand the second graph? I'm not able to interpret it. Like, how is
So,
H increasing with sigma 1 and sigma C?
right. So, let's say at this H, this is sigma C and sigma 1, right? And this ratio, let's say this is 1 let this is 1 and this will be 1.2. Assume that. And so at this height, and this will be, if it is close, maybe 1.5. So FFC at this height will be 1.5. Let's say at this height, and this is 1.5, maybe this is 3. Then the ratio at this height, I'm not putting exact numbers, but just to help you. And this is the 2. 1.5 by 3. 2. Do you understood now?
Yes, sir. Yes, sir.
Otherwise, I can repeat.
Yes, sir. Understood.
Okay. So, the important concept I've explained today, the most important or two main messages is, one is how to minimize the addition forces to enhance the superhydrophobic nature or to enhance the flowability. Another one is from understanding of unconfined yield strength, that is the maximum stress at which the particles tends to flow or the compacted source tend to break, both are same. So the vertical load what we are applying in silos should be higher than unconfined yield strength. So
Sir,
if the load, yes.
sir, one doubt in this graph, like the sigma 1 value that we are giving to the particles inside the cone, like
Yeah.
will it not be the highest at the bottom? Like suppose some force we are giving from top band, or at the bottommost point the load of the weight of the particles also adds up to that force. So like sigma 1 should not have been some high value at h equal to 0, and then constantly decrease to some constant value at h equal to x.
I understand your point. Suppose when we store solid, definitely the bottommost point will have the highest load, right?
Yes, sir.
Yeah, that is perfectly right. Just for the explanation point of view, right? Let's say we are taking H in this direction, and here, okay. I think what I want you to convey, what I wanted to convey here. One is, let's say you have an empty silo. We have an empty silo, right? And the particles are packed. The particles are packed. So the particles are stationary. Now, as soon as you wanted the particles to flow downwards, as let's say as soon as you open the rotary valve, whatever, the particles will tend to flow down. The particles will tend to move out, right? The particle will tend to move out. Now, the rate at which the particles will come out, the stress with which the particles come out will be opposite of the load. The nearest particles will come out with easily. The nearest particle at the discharge outlet particle will come out easily, right? You are exactly correct that the load on the particle is higher at the bottommost point. Now, when we see from the flowing conditions, the particles tend to come out, right? The particles near to the outlet will come out easily. So, just for, I think we can plot the same graph in the reverse direction. That is, at this point, value is 0, and you will get the same prevailing conditions. Now, what I want to represent is, let's say we have taken from 0 and no flow is taking place. Hence, the force with which the particles are coming out will be 0. That is what I wanted to represent here. I'm just putting the reverse one, flowing conditions. I'm
Yes,
not
sir.
putting the storing conditions.
Yes.
This okay. Another important I want to say is, this is an hypothetical way to make you understand that why it is important to have the load is higher than a unconfined yield strength. That is only to illustrate that point only I have explained this graph. Hope you understood.
Yes, sir.
Yeah, thank you. So in silo design, two things are important. One is totally three things important. One is the material. First one is what is the outlet opening? What is the outlet opening? It has to, there is some, it has, and also what is the angle of this one? What is the angle of this one? This opening's diameter and this angle determines the flowability, how easily the particles can flow. Whether it is mass flow we are achieving or whether we are facing any flow obstructions. These are the two important. So these are depends upon very few other parameters. Another important thing is we need to understand, let's say we have used certain material, right? We have used certain material with certain thickness. Let's say we can use stainless steel, mild steel, or concrete. We can use different materials. Each material will have a maximum yield strength. Each material will have a maximum yield. Just like solid materials, the material used for the construction of silo, also will have the maximum yield strength. So hope you all understand what I'm trying to say. Suppose we have a metal bar, right? If you apply certain load, let's say if you apply very little load, it will not deform, it will not bend. But if you apply very high load, what will happen? It will tend to bend. Initially, there will be some bending. If you keep increasing the load, what will happen? At some point of time, if you cross the maximum bearable load, then permanent deformation can take place. So just like solids, even this material used, that is also solid material, that will have the maximum yield strength, right? So when you store solid particles, when you store solid particles in silos, the load, okay, the gravitational force or external load, what you're applying, that is also subjected to the walls. The maximum load offered by the maximum stress offered by the solids should be less than maximum yield strength of the solid material. Maximum yield strength. This is yield strength, right? Yield strength of, yes, yield strength. Maximum yield strength of the material. Okay, with what material you are constructing the silo. Material. This should be higher than, right, the maximum stress offered by the bulk solids. Maximum stress offered by the bulk solids. Am I right? Suppose if the maximum stress offered by the bulk solids is higher than yield strength, what will happen? Suppose, let's say, instead of this has happened. The maximum stress offered by bulk solids is higher than maximum yield strength. What will happen?
Bending of silo, like buckling.
The binding will strength or deformation happen. It can break if it is a pressile material. So we need to find out what is the maximum stress offered by the bulk solids, and that should be, or we have to find out. So we have to choose a material of construction should have higher yield strength than this one, right? That is the first condition. Second thing is that the angle of Hooper and the outlet diameter is such that you will get a free flow. So these are the three important factors in the to get the mass flow conditions in the silos design. Right. So another important, this is the last factor. Sorry to put lot of text here, but I will not bore you because I kept some graphs to make you understand. Another important factor in solids storage is time consolidation or caking. Right? Some bulk solids, please, some bulk solids continue to gain strength if stored at rest under compressive stress for long period. Right? I explained before, right? If you this is a silo, and if you store the particles, and because of the gravitational force, some load always acts on the particles, right? Because of this continuous load, that is nothing but the compressive stress, because the load is actually compressing the solid particles. If you store for a long period of time, the whole bulk solids will gain strength. That means unconfined yield strength is increasing with time. Unconfined yield strength is increasing with respect to time because it's gaining more strength. That effect is called time consolidation or caking. What are the so before reading out all these things, let me give some example. Okay, so this is the gypsum. We all know gypsum material, right? The gypsum is very sensitive to the moisture. If the gypsum has 0.2 moisture content, if you store 50 hours, 100 hours, 150 hours, you will not see the variation in unconfined yield strength. Unconfined yield strength is constant. Instead of 0.2%, if the moisture content in the solids is 1%, what will happening? The unconfined yield strength is increasing and stable after some time. If it is 2%, the unconfined yield strength become more. If it is 5%, become more, and if it's 10%, it is reducing. Become like a more or like a suspend. Is formed like a suspending. So why is this happening? When you have moisture solids, right? This is wet solid, and this is wet solid, and this is wet solid. If you apply some load, if you apply some force, what will happen? Can anyone guess? We have moisture solids. This is moisture, this moisture, and we are applying some load. What will happen? These all particles tend to come closer and become more and more sticky. More and more adhesion takes place. So the interaction between particles increasing. Interaction between particles are increasing. They're gaining more and more strength. So the unconfined yield strength is increasing because of the interaction between the wet solids. So when the sigma c is increasing, we have to know that we have to apply more and more. We have to apply more and more vertical stress for the flowing conditions. If it causes sometime this increase in unconfined yield strength can lead to the stagnation zones. This can lead to the agglomeration stagnation zones. So this is called time consolidation. With time, the solids getting compressed, consolidated, the strength getting increasing. This is another example. This is another example. So here they have stored. They're taking the sulfur. They've taken the sulfur. They have seen the effect of temperature. They have seen the effect of temperature. Okay. So they have stored the sulfur in a silo, and at 20 degrees centigrade, they have observed that there is no increase in unconfined strength. When increase in 30 degrees centigrade, there is no increase. But when it crosses 40 degrees centigrade, the unconfined yield strength is started increasing very fast, very rapidly. So if you maintain higher temperatures, whether due to weather conditions, right? You know, sometimes we can have in summer, you can have the temperature higher than 40 degrees centigrade. Then more and more consolidation, compaction takes place if you store in the sulfur. This is the keeping the storage time constant. Okay, here they kept the storage time constant. Of course, they can vary storage time at 1 degree. You will get definitely that unconfined yield strength increase. So what happens if the particles of low melting temperature, the particles, not necessarily any particle, okay, if any particles, if the temperature of the surroundings is close to the melting point, not necessarily same, it's close to the melting point temperature, what will happen is most often, because the atoms, once it is melting point, it become like liquid, right? So the movement between atoms will very loose. It can be very high. So when the temperatures are close, not same, right? Close. Let's say this is 80 degrees centigrade, temperature 60. Then what happens is that there is called sintering effect. Sorry, sintering effect. What is the sintering effect? Sintering effect. Oh, not finished silo design today also. Sintering effect. What happens if two particles are placed each other? If the temperature is slightly less than melting point temperature, what will happen is that if you leave it for some time, the atoms, the particles tend to join to each other because of the high movement of atoms in the solids that can lead to the more adhesion between the two particles. That happens only if the temperature close to the melting point temperature. Suppose if you take one example I will give. Let's say we have the gold particles. Let's say these are all the gold particles. We have just placed on a flat plate. Right? If you maintain temperature slightly less than melting point temperature, what do you observe? Instead of becoming the gold turn to the liquid form, right? What will happen because of this atom movement, the strong interaction between all the particles, you will see that all these individual particles will form as a film. You will see a nice gold thin nanofilm you will find out. That is because of sintering effect. So when you heat higher temperatures, in a silos also, or in the atmospheric temperatures higher enough for the solid store, this consolidation, interaction between particles will increase, and that will increase the unconfined yield strength. Okay, so I have given two examples. One is effect of moisture and the effect of temperature. So these are different. Sorry. Hello. Someone want to ask question, or did I make some mistake? Are you saying time is over? Is that? Probably not for me. Yeah. So different possible mechanisms for this time consolidation are taking. I have listed out. The solid bridges due to solid tend to crystallizing. Like initially, let's say more moisture is there. As you store, the particle tend to dry. During the drying, there is a solid crystallization taking place. And solid bridges can form during the drying. And bridges due to the sintering. And due to chemical reactions or chemical interactions, due to biological interactions like fungal growth, can enhance the interactions between the particles. So that's what important factor. If some material tend to do this time consolidation very faster, such material cannot be stored in soil for longer time. Or we can from this time consolidation studies, we can say how many days we can store, what are the effects. All of them can be understood from this time consolidation. One important thing, this time consolidation is predominant when you have the fine bulk solids. Fine bulk solids, hence it shows the poor flow behavior. Fine bulk solids cannot be stored for a long time in the silos. If you want to store it, we need to blow some gases through that. We need to blow some gases continuously through that. That is called flowing agent. When you blow this flowing agent through this silos, that will make sure that unconfined yield strength, or FFC, will be remain same. That will make sure the FFC remains same. So these are all different effects, factors talked about this one. Sorry, I had to keep a theoretical lecture because I wanted to explain various factors. These are all simple and important concepts when you understand the flow behavior. So in the next class, we will see how to find out the I have told three factors, right? What is the maximum stress acts in a solid particles? We will derive this derivation, very, very simple. You don't need to worry by seeing the slide. It's a very simple derivation. We'll understand what is the stress profile in a silos. Then we'll understand how to estimate the angle. Then we'll understand how to estimate the outlet diameter. Then we'll solve 2 to 3 problems in the next class. So that's all for today. It's already 9:58. We might be having next class. If you have any questions, you can ask me. Otherwise, you may meet for the next class. Yes.
Sir, I have a question. Sir, did you mention the name of the gas that we have to pass in silos to prevent?
I haven't mentioned. Different depends on the material. The gases will vary. Often, like if we have a sulfur, coal, we always use nitrogen, but that depends on the material to material. So the material property is that should not interact with solid. That should only take away the moisture or any moisture between the particles. That is the only prime reason. Because liquid bridge between the particles can lead to this time consolidation.
Okay, sir.
Thank you, Aditya. Any other questions from any other student? If you do not have questions now, you may revise my slides. I will upload. You can ask me questions next week. But my request is please read as you learn. So suppose today my class, just spend half an hour today evening, just review my slides. Then that will stay with you for a long time, right? Okay. Thank you guys. Have a great day.
Thank
Thank
you,
you,
sir.
sir.